Here we go again, everyone. This is our video solution to problem 3 from Superquiz 2. This is the problem that proves Dr. Glesser really is not a nice guy. So we're asked to compute the Laplace transform of a function. The function is a piecewise defined function, and we're told we need to use the definition of the Laplace transform. And what the heck is this thing up here? And does it even matter at all? All right, well, let's take a peek here. So the definition of the Laplace transform, right? That's key here. Look at the small cap text, right? Like that's really trying to stand out. We want to use the definition, and the definition says you're going to integrate from 0 to infinity the function at t times a decaying exponential. And what we should recognize right off the bat is that when we integrate from 0 to infinity, the function is irrelevant before you get to 0. So this -5 to -2 that looks so scary and terrible, it doesn't come into play, right? This we could just ignore. In fact, from -2 all the way up to 0, that doesn't really matter, right? We might as well just make this 0 to 5 instead of -2 to 5, because the Laplace transform cannot see what happens to the function before you get to 0. Now, once you get to 0, now we have a little problem, right? The function is defined differently from 0 to 5 than it is from 5 to infinity. So what we'll do is we'll break the integral up. We'll go from 0 to 5. And when I'm between 0 and 5, the function is just the constant function 4. So I'll have 4e to the -st. And then I'll integrate from 5 to infinity. All right, ooh, nice improper integral. And on that interval, my f of t is t. So I'll have te to the -st. So I actually have two integrals to compute here. Okay, we got some work. So this first one shouldn't be so bad. Let's see here. So 4e to the -st dt. I need to find an antiderivative. Okay, this 4 doesn't concern me. I'll just copy it. An antiderivative for e to the -st, and we're integrating with respect to t, is going to be, well, e to the -st, and then I have to divide by this coefficient in front of the t. So I'll divide by a -s. I'll pull this negative out front. And then I'm going to integrate right from 0 to 5, so I need to evaluate at 5 and at 0. So at 5, I get -4 over s times e to the -5s minus, okay, and what happens at 0? At 0, I get -4 over s, and then e to the 0, which is just a 1. Okay, so in total, it looks like I get a 4 over s in both of these terms. I could pull that out. This was minus, that actually was a +1. So what do I get? I get 1 minus e to the -5s. All right, so that's what this first bit is going to be. And what about the second bit? All right, so we're going to integrate from 5 to infinity te to the -st. That definitely screams out integration by parts. So let's give it a try. I'm going to use the tabular method. I'll have a t and an e to the -st. And this is very similar, actually, right, to problem 2a from this super quiz. So I differentiate until I get to 0. So t1, 0. And then I'll anti-differentiate just as many times. This -s, that's the constant that's going to be divided by each time. So I'll get -1 over s, e to the -st, and then 1 over s squared, e to the -st. Okay, again, when I divide by -s, again, the negatives cancel and I get an s squared. All right, I draw my lines, plus, minus, and so my antiderivative, let's see, I have an e to the -st. I just pull that out. And then I'm going to have -1 over s times t and -1 times 1 over s squared. Might as well pull the negative out too. So I just have to worry about t over s. and then 1 over s squared. And now I have to evaluate between 5 and infinity. Okay, so the infinity part, what's going on? I have a decaying exponential, and so as t goes to infinity, this guy should decay to 0. Okay, well, what about in here? Well, the 1 over s squared is a constant, but ooh, t over s, as t goes to infinity, this blows up to infinity. So I have something decaying to 0 and something blowing up to infinity. Who wins? Well, we've discussed this, several times before, right? Exponentials decay to 0 faster faster than polynomials grow to infinity. Okay, that's the general rule that we are using. How did we get this rule, right? Well, we use L'Hopital's rule, right? So we have something going, this is going to infinity, this is going to 0. Of course, you could put this in the denominator and say, oh, now I'll take a derivative because they're both going to infinity. All right, the polynomial is going to die, the exponential never does. Okay, so the first piece of this is actually just going to be a 0. Then we get a minus, and okay, we have negative e to the negative 5s times 5 over s plus 1 over s squared. Okay, and of course this minus minus will cancel, and we have e to the negative 5s times, I'll just leave it as it is, 5 over s plus 1 over s squared. All right, so if we wanted, we could now plug these back in here for our answer. I'm kind of bored, I don't want to do that. So we've written it separately, that's quite fine. So you just add these two answers together and you get your final solution. All right, I know, it wasn't a nice thing to do, but it's really important, right? When you use a definition, you got to understand, right? That all the concept of the definition. The Laplace transform doesn't care what your function does before 0. It only cares what happens once you get to 0. All right. All right. We'll see you next time for problem 4.